Alrighty, hello everyone. First of all, I am so sorry for the late delay for posting this part two of discussion number 11. I've been super ill since discussion last week. I actually came down with bronchitis and the flu. So I have been completely incapacitated. I have had no voice, and today's the first day where I have somewhat of a voice so I can get this recorded. So this is actually my sixth time to record this. There have just been many errors in all of my recordings, lags. My iPad pin is not working too well. So hopefully this recording goes well and I don't have to start again because I've been sitting on my floor for about 2 hours and 13 minutes trying to get this 20-minute discussion video recorded. So fingers crossed we can make it through this time. But yeah, so again, last week we started with the physiology behind the renal system, looking at the physiology of the nephron. We looked at those four processes, renal processes, which was filtration, secretion, reabsorption, and excretion. So today we're going to actually use all of those and do some math. So I'm going to share my screen and move over to my iPad so we can work through these last few calculations together. So as you see here, I have the questions to one side and then our equations and our givens to the other side. However, on the exam, you will not get this nice little equation sheet. You do need to have these equations memorized. So make sure you do something to where you have these down. I'd recommend printing out the worksheet or using some scratch paper and working through these problems a couple times just so you become comfortable with the equations. Because they're not very hard once you get them. They're very simple equations. There's no calculus involved with them. It's all simple algebra. You just need to understand the variables and how to manipulate the equations to get the answer that Dr. Chang will be looking for. So make sure you do not go into exam 2 without knowing these equations because they will not be given. So you do need to memorize them. All right, so let's go ahead and begin. Question A is asking us to use creatinine clearance to estimate the patient's glomerular filtration rate. So we're solving for GFR using clearance, specifically clearance of creatinine. So normally we will first solve for GFR or it'll be given because it's very useful in all of the other equations. So let's go ahead and do that. So if you look over, or if you haven't memorized, which would be awesome, we do have an equation for clearance. We have a clearance equation. Oh my gosh, here goes this pin issue again. So clearance equals the excretion rate, and we're specifically looking at creatinine. So the excretion rate of creatinine, which I'm just going to abbreviate as CRE, divided by the plasma concentration of creatinine. So let's go ahead and see what we're given and see if we can solve this. So urine flow, no. Plasma concentration of creatinine, yes. So we do have this bottom variable. However, if you look at the rest, we do not have the excretion rate of creatinine. So we're going to need to use another equation to be able to solve. So we have two equations for excretion rate, number 2 and number 4. However, if you compare the values that are given to those two equations, the second equation, number 2, would be the best to use. So that equation is excretion rate of creatinine equals urine flow times the urine concentration of creatinine. So we are given urine flow right here, and we are given the urine concentration of creatinine. Make sure you're looking at the correct concentrations and the correct, areas. We're looking at the urine, not the plasma right now. We're looking at the urine. So 2 liters per day for urine flow. Oh my gosh, I'm getting so mad with my iPad. Times the urine concentration of creatinine, which is 75 milligrams per liter. When we solve that out, what we get is 150 gram or 150 milligrams per day. Those liters cross out and we are left with milligrams per day. So that tells us that we are excreting 150 milligrams of creatinine in our urine per day. We are urinating out 150 milligrams of creatinine. So now that we have our come on, pen, our excretion rate of creatinine, we can now go and plug that into our original equation. So what we get is 150 milligrams per day divided by our plasma concentration of creatinine, which we look over here, plasma concentration of creatinine, which is 0.1 milligrams per deciliter. What we get is 1,500 deciliters per day. 1,000 deciliters per day. Those grams are going to cancel out. If we want to put that in a more understandable unit, that is the same thing as 150 liters per day. So we can, our GFR is either 1,500 deciliters per day or 150 liters per day. So that is how much our glomerulus is filtering, how much blood our glomerulus is filtering per day. So GFR. So we can go ahead and add that over here. Our add that over quickly. Our GFR equals 150 liters per day. Awesome. So we have now solved for question A. All right, so moving on to B. So B is asking us how much glucose does the patient filter per day. So per day tells us we're looking at a rate, and we're specifically looking at filtration rate of glucose. So this tells us that we are looking for the filtration rate of glucose. So we look over to our equations and we do have an equation for filtration rate. So filtration of glucose, the filtration rate of glucose is equal to our glomerular filtration rate, which we just solved for, times our plasma concentration of glucose, because we're now working with glucose, not creatinine. Luckily, this equation is pretty simple. We have both. We have our GFR and we have our plasma concentration of glucose here. So what we're going to do is we're going to take 150 liters per day and multiply it by our plasma concentration of glucose, which is 400 milligrams per deciliter. So we want our units to match up. So we're not going to use that 150. We're going to use that 100 or 1,500 deciliters per day. So make sure you're using the correct units or they will cancel out. You could do 1,500 times 400, or you could do 150 liters divided by 440 liters per deciliter, or whatever. I would use this method So when we solve this out, what we get is 600,000 milligrams per day, because those deciliters will cancel out. This is the same thing as, oh my goodness, same thing as 600 liters per day, or sorry, grams per day. So that is our final answer, telling us the filtration rate of glucose. So this is how much glucose we are filtering per day. So filtration, oh my gosh, rate of glucose, F. All right, so filtering 600 grams for glucose. That's a lot of grams of glucose to be filtering a day. Wow. All right, so C, how much glucose does the patient excrete per day? So per day, we're looking at a rate, we're looking at excretion and glucose. So this tells us that we will be solving for E GLU, the excretion rate of glucose. Again, anytime anything's in a subscript, that means rate. If it's in brackets, that means concentration. So let's go ahead and look at our equations. So we actually have two equations for excretion rate. We have excretion rate equals urine flow times urine concentration, and we have excretion rate equals filtration rate minus reabsorption rate plus secretion rate. And if we look at our givens, we're not given filtration rate, we're not given reabsorption rate, and we're not given secretion rate. However, we are given urine flow and urine concentration. So let's use the first one. So excretion of glucose is equal to urine flow times urine concentration of glucose, because we're working with glucose. So luckily we have both of these. We have urine flow per day, and we also have the urine concentration of glucose. So when we solve this out, what we get is 2 liters per day times the concentration of glucose in the urine, which is 37.5 grams per liter. And when we solve this out, what we are left with is 75 grams per day, because those liters will cross out. So that is telling us how much glucose we are excreting in the urine per day. So this is glucose excretion per day, or excretion rate of glucose per day. So taking this into mind, you need to make the association that excreting glucose in the urine is not a good thing. That's kind of a sign of diabetes or not good health. So this tells us right here that this person is surpassing that renal threshold. They've hit that Tmax, and they're having glucose in the urine, which is not good. You do not want glucose in the urine. You want to reabsorb all the glucose that you take in to be used for energy. If you're taking too much glucose in, it's going to start showing up in the urine, which is a bad sign. So this tells us, this is not good. This value should be 0. If it's above 0, that tells us that there's some type of issue going on. We should not be excreting glucose in the urine. So moving on to question D, now we are looking for Tmax. So we have an equation for Tmax. It is Tmax equals GFR. Let's just write GFR times renal threshold. Well, we know our GFR, but what about our renal threshold? So I want to go back to this chart to kind of work through this question. So we know that we have already hit our renal threshold due to this right here. Since we are already seeing glucose in the urine, that tells us that we have already surpassed this point. So that urine concentration was given as 37.5. Oh my gosh, this pin, 37.5. So since we already have some glucose in the urine, that tells us we've already surpassed this point. Whenever we hit renal threshold, that's the point where Tmax occurs. And we know that this relationship exists. Oh my gosh, no, this happened right before. Hopefully I can fix this. Oh my gosh, okay, hopefully that's fixed. I do not want to record this video again, but okay, hopefully this works. So what we see is that we reinstate this fact that reabsorption rate of glucose is equal to Tmax, because when Tmax occurs, that's the max amount of glucose that we're going to be able to reabsorb. We can only reabsorb, so oh my gosh. Hopefully this works. So I think that slide was kind of messing with the broadcasting, so I'm just gonna have to go back to this. So we know that we've already surpassed the renal threshold because we're Because we're already seeing glucose in the urine, So we are not given the exact renal threshold. We know that there's glucose. We know there's 400 milligrams per deciliter of glucose in the plasma, but we don't know at what point that is. We don't know what point on that graph is. So we're going to have to use another equation to solve for T max. However, we only have one equation for T max, which I have written here, and it involves renal threshold. However, that relationship of T max equals the reabsorption rate of glucose can be used. So what we're going to use is excretion rate of glucose equals the filtration rate of glucose minus the reabsorption rate of glucose plus the secretion rate of glucose. And again, that reabsorption rate, we can set reabsorption of glucose equal to T max, because T max is the max rate that we can reabsorb glucose. So that relationship exists. My iPad's giving me a lot of issues. I'm so sorry about this, but I can't record it on paper because you wouldn't be able to see what I'm writing. And then we also already solved for the filtration rate of glucose over here. I forgot to write that value. Filtration rate of glucose equals 600 grams per day. And what was the other value we solved for? Excretion rate of glucose equals 75 grams per day. So when we return to this, what we see is that we have our excretion rate of glucose. We have our filtration rate of glucose. We need to solve for T max because we do not have the reabsorption rate of glucose. And then we're left with secretion of glucose. Now there's something very important to know about glucose. In our four processes of the renal system, we have filtration, reabsorption, secretion, and excretion. Glucose will never be secreted. It will never be secreted. If we go back to this picture way at the beginning, we see we have filtration, reabsorption, secretion, and excretion. And secretion is dealing with moving molecules from the bloodstream into the nephron to be excreted in the urine. However, we never want to remove glucose from the bloodstream because we need to get glucose to the muscle cells so we can use them for energy and create ATP. My iPad just went out again. So secretion of glucose never occurs. Excretion of glucose can occur because it can be excreted in the urine, but physiologically, we're never going to secrete. Our peritubular capillaries are not built to secrete glucose. They're only built to reabsorb glucose from the nephron. They will never secrete glucose from the capillaries into the nephron. They can only reabsorb glucose. So what that tells us, and I realized my screen share kicked me off again. To rejoin the meeting. What that tells us is that the secretion of glucose is 0. We will never, ever, ever secrete glucose. So we can just set that to 0. So now let's go ahead and, solve. So again, we're looking for T max. So if we manipulate this equation, T max, which again, we know is reabsorption of glucose, is equal to, whenever we flip this over, we would get this moving over here. So this would be filtration of glucose minus the excretion of glucose. Just manipulating that equation, moving the variables around, which leaves us with the filtration of glucose, which we solve for over here, as 600 grams per day minus the excretion of glucose, which is 75 grams per day. And what we get is 525 grams per day. So that is our T max, This is the max amount, or the max amount of glucose that we can reabsorb per day, or the max amount of glucose that we can transport per day in the nephron. But we know that we, took in more than that. We took in 600. We filtered 600. So our kidney, our glomeruli filtered 600 grams because we intook 600 grams of glucose. However, our max rate is 525 grams per day. So that is our T max. All right. So now we're solving for renal threshold. Why isn't it showing words when there should not be words? There we go. So renal threshold, we're just going to use that same Tmax equation, but now we have Tmax. So we can manipulate this equation to get that renal threshold. So we're solving for the renal threshold. We have both of these. So we'll manipulate it to be renal threshold equals GF, or renal threshold equals, sorry, Tmax divided by GFR. When we do this work, our Tmax that we solved for was 525 grams per day, divided by our GFR, which was 150 liters per day. So what that tells us is that we will get 3.5 grams per liter, or 350 deciliters, or milligrams per deciliter, sorry, milligrams per deciliter. So that is our renal threshold, That is the concentration of glucose in the plasma. And once we surpass that concentration, that 3.5 grams per liter, we will hit that renal threshold and no longer be able to reabsorb glucose into the bloodstream. We will begin excreting it in the urine. All right, so last question, calculate the patient's glucose clearance, and then what is normal glucose clearance? So we're looking at glucose clearance. So we're gonna use our clearance equation here that we used for part A. So clearance equals excretion, and now we're dealing with glucose, not creatinine, divided by plasma concentration of glucose. So we have both of those values. We have excretion rate and plasma. So we just will simply plug those in. So our excretion rate of glucose was 75 grams per day, and our plasma concentration of glucose is 400 milligrams per day. So let's go ahead and convert that 75 grams into milligrams. So when we do that, we get 7,500 milligrams per day is our excretion rate glucose. And our plasma concentration of glucose is that 400 milligrams per day. So when we solve this out, what we get is 187.5 deciliters per day. So that is how much, wait, where did I get deciliters? Sorry, this should be deciliters. So what we get is deciliters per day. Those milligrams cross out and we're left with milligrams per deciliter. So that is how much glucose we are clearing. So whenever we discuss, what a normal glucose clearance would be, normal clearance of glucose should be 0. We should be clearing no glucose in the urine. We should be reabsorbing all glucose into our body to use it for ATP breakdown and energy production. So a normal glucose clearance, I'm not going to write it out because my iPad pen is just not working with me today. Normal equals 0 deciliters per day. So this tells us that this person has some type of disease where their kidneys are not reabsorbing glucose to be used for energy. So lastly, I just wanted to add this in here and talk about how does the kidney handle glucose. So if we compare our glucose or GFR to our clearance, we see that the glomerular filtration rate is higher than the amount we're clearing. So that tells us that filtration is greater than um, secretion, which means we. I'm not sure I understand. I'm having so many issues. I'm sorry. That tells us that we reabsorb glucose. So the net process is net reabsorption because we're filtering way more than we are secreting. Um, so yeah. Yeah, guys, thank you so much. Sorry for all the technical issues, but that is it for renal math. Definitely practice that a few times. I think I had some announcements finishing up. I announced these at the beginning of the last lecture, just a little reminder. But yeah, y'all have a great Thanksgiving, and I will see y'all for discussion 12, our last discussion before Thanksgiving. So I guess I'll tell y'all happy Thanksgiving next time. Having issues today. Thank you. Bye.